All right, so we're going to do Chapter 8, which this will catch us completely back up. 8 is the only one that I did not have pre-recorded, and 8 is on wireless. There's not a whole lot on the test about wireless, but the things they do want you to know are how wireless networks communicate, and then know the different speeds and the numbers and the frequencies. Like, make sure you know the differences in an A, a B, a G, and an N network. You might get a sprinkling of the new one called WiMAX, but there's not a whole lot about it. WiMAX is kind of a new long-range technology they're working on, and the plan with WiMAX is now we've reached a point where almost everyone in America has an option for high-speed internet now. But you have those few people that live like in farms in the middle of Iowa where they don't want to run wire because, you know, it's 10 people. It doesn't make sense to run wire. That's where this WiMAX stuff is going to come in. You put up a small tower outside their house, like a little TV tower you'd have an antenna on, and put a WiMAX antenna on it, and you can send a WiMAX signal 30 or 40 miles. So that's going to be the way that we get high speed into these very last places where we don't have it. So we can talk about how the nodes exchange signals, the potential obstacles to wireless, and we're going to talk about WLAN, which is wireless LAN architecture. We'll also specify the characteristics of a WLAN. We're going to talk about A, B, G, and N. They're all the 802.11 standards, by the way. That's wireless, or at least that's traditional wireless. And then we will talk about WiMAX. I'll sprinkle a little bit about LTE, which is, you know, your 4G networks. And those are becoming more important now because in the 3G world, phones were slow. But now with 4G, a 4G network standing still is just as fast as any other wireless technology, so it's something you've got to deal with. I think that one thing that some of the phone companies have done that's a mistake is by putting bandwidth limitations on their networks. I think had they not done that, people might have actually looked at them as a way to get a wireless network connection. I know, like where I live over there in Broadmoor, I could get one of those Verizon hotspots, and it would be faster than DSL. But they put a 20 gig a month limit on it. I go through 20 gigs watching Netflix. So, you know, that makes it not something for me because I know I'm going to use it all. If they hadn't put a 20 gig limit on it, however, though, I'd probably look at that as an actual network option versus going with cable or any of these other ones. All right, so we have the wireless spectrum, which is the continuum of electromagnetic waves, voice, data, everything ends up in this spectrum, visible light, microwaves. Basically, the entire electromagnetic spectrum is everything that we transmit in any sort of way. They say it spans 9 kilohertz to 300 gigahertz. It actually doesn't have a beginning and end, but this is the part that we know about. It can go way beyond 300 gigahertz, and there are signals down below 9 kilohertz. We just don't know much about them. Wireless is associated with one area of that. In the United States, the FCC oversees who gets what frequency. In all of the rest of the world, it's a group called the ITU. And the FCC and the ITU do work together, but this is also why you can't take a cell phone from here, and if it's not a world phone, it work anywhere else. They use different frequencies than we use in all of the rest of the world. Leave it up to the United States to be the ones that are different at it. But that's also why some areas get phones before we do, because they'll make a new phone and they'll release it in these other countries because more people can use it there than here. And one more thing I'm going to point out about here, the reason for the ITU, you know, in the United States, we're kind of isolated. I mean, we've got Canada and Mexico, but we're not lots of small countries. Wireless doesn't just stop at a border. You know, you don't just go to the Canada-US border and the wireless signals just stop right there. So the ITU is important in these smaller countries because one cell phone tower might easily propagate into other countries. Here's just kind of an example of some of the important things in the wireless spectrum. From 9 to 100 kilohertz, you've got radio navigation, marine, and aeronautical. Some of your airport beacons are in that area. AM radios above that, and then in the 10 megahertz, which is also called 10 meters, you've got shortwave radio. CB is 11 meters. Above that is FM radio, and then old television signals were above that. Then you get into L-band satellite and cellular and WiMAX. L-band satellite is some of your stuff like DirecTV and Dish Network and those. C-band satellite, those were the old dishes. I don't know if any of y'all ever had anybody that had one of the big old dishes. Where my parents lived in Spring Hill, they didn't have cable. Cable wasn't an option. They had a C-band satellite. And I remember each satellite had 24 channels on it, and if you wanted to change it to another 24 channels, you literally had to go outside and crank it. And my dad had got these two little handheld CBs from somewhere. So what you had to do was somebody would go out and crank it and listen on the CB, and when the next satellite would come into signal, you know, they'd say stop or go back a little to change the satellite. And now, you know, you've got things like DirecTV that's got no telling how many actual channels on it now, and it's all on one satellite, or a couple of satellites in the same line. Your wireless LANs also fall right there at 2.4 gigahertz. KU and KA band satellite and WiMAX are up at around 10 to 15 or 20 gigahertz. KU and KA basically are still used somewhat today. Those are the uplinks. That's when you send, that's what frequencies are used to actually send the TV channels up to the satellites. Your satellites that communicate with like some of the things that we've sent out like Voyager, all of that's done with old KU and KA band, because that was, you know, now it's kind of outdated, but that was the best technology they had at the time we launched this stuff several years ago. And then you can have some satellite stuff up into 100 and 300 gigahertz. Some of the weather satellites are up here. Doppler radar, I think, is somewhere up in that high range. And Doppler works by actually sending out radio signals, and they bounce off of the moisture in a storm. That's how they're able to get back information. It does it very quickly. That's also why, though, if you look at like Doppler of Shreveport before they edit it, you see what's called ground clutter, where the buildings downtown that have water pipes in them, those water pipes have sent signals back. So you have to clean all of that off before you can look at a Doppler radar image to figure out, you know, where, pardon me, where the storm is. All right, so wireless shares a lot of characteristics with wired networks. Some of those, it uses layer 3 and higher protocols. At least the similarities are in the layer 3 and higher. IP is IP no matter how you transmit it. The signal is originated in the same way. Wireless doesn't have a wire to it, but usually the wireless is tied to some wired network, and the signal was generated on a wired network and then sent to wireless. The differences are in how the wire is transmitted. In the actual wired world, you know, the path of the signal is determined by where we put the wire. In wireless, it's just sent out there. In fact, if it's sent in an omnidirectional antenna, which most use, it just goes all the way around it. The antennas we have back there, they're omnidirectional, so the signal is going to be the same all the way around the room. All right, so here they're just showing an example of that, and here they're showing two wired networks hooked together with wireless. Okay, so antennas have a radiation pattern, and the two big ones are directional and omnidirectional. Most default applications use an omnidirectional antenna. That means the signal is sent out in all directions. You can get a directional antenna, though, and that tends to make the signal more focused, so it'll go a further distance. Like if you do a little bit of research on the internet, you will find plans to make a wireless antenna for your ABG and N networks that uses a Pringles can. And MIT does a test every year. They run a contest to see who can send a 1-watt signal the furthest by coming up with different antenna designs. And the winner right now is, I think, the Pringles can antenna, and it sent the signal, I think, 30 miles. So it's a tremendously, gain you get off of that. And the whole idea of the Pringles can is, you spent $10 to build this antenna. You literally put the antenna in a Pringles can. I've heard of people that live on, like, a lake doing that and pointing a signal all the way across the lake because it's open, there's not any trees. So you can get a signal all the way across the lake doing that. If you've got a cabin on one side of the lake and you live on the other, well, there's no reason to buy internet over there. Here's your antenna. And you also classify them by range. Different types of antennas will give different ranges. So with most wireless, you have what is called line of sight. And that means the signal travels in a straight line and it's directly from a transmitter to receiver. Line of sight is used in, like, television and telephone microwave towers, where you've seen the horned antennas they put up on a tower, and there may be a tower that's got one on the east side of it and one on the north. Well, the purpose of that tower there is actually to turn the signal. They got that there to receive the signal from one side and send it back out in another direction. And those are up high because most of the microwave stuff is line of sight. A tree gets in the way. You got to get up above the trees for it to work. The other problem you have of that with those straight line ones is that the earth is actually curved. The signal would go a lot further, but you've got to have different height antennas because the curvature of the earth, when you start talking about like a 30 or 40 mile range, is actually noticeable. There's a video, and if I can find it, I'll post it in a Blackboard for y'all. It's kind of fascinating, at least it was to me. A guy is replacing a light beacon on the top of a very, very large tower. I think it's in Canada. It's one of the world's largest TV antennas. It's, I think, 1,700 feet or 1,700 meters up. And he put a camera on his hard hat to show what his day was like for people to watch. And at that height, it's kind of funny. You can actually see the curvature of the earth. He's up high enough, you can see that it curves down around everything. But that becomes important when you're dealing with wireless, because you got to, if it's straight line, you got to get it through there. Now, when an obstacle is found, either the data will pass through it, it's going to be absorbed by it, or it's going to be subject to reflection, diffraction, and scattering. Reflection bounces it back to the source. That's how radar works. You send a signal out and it bounces back and it tells you how far away the object was. Then you send another one at another point in time and see how far it traveled to determine the speed of something. Diffraction is where it splits into secondary waves. And then scattering is basically like light in a mirror, multiple directions. It goes in all directions. All right, so one thing with wireless is that the paths will follow different. The wireless signal will follow different paths to the destination, and the reason for that is reflection, diffraction, and scattering. The advantage is you have better chances of reaching the destination. If we had a multi-directional antenna in here, I said it would go all the way around, but it also goes up and down. The signal is going to bounce off the walls, the ceiling, the floor, the computers, each of us in here. There's a higher chance of the signal reaching our point that it needs to go to, though, because of all these directions. But the signal's not always going to get there at the same time, so you've got to deal with signal delay. Here's their example showing just that. You've got a wireless access point, and it's scattering off a wall, it's reflected off a ceiling, it's being diffracted by a table. So basically, you covered the area in signal, but it's all in different pieces. So one thing that happens to wireless signals is fading, and fading is when you get a variation in the signal strength. It can be caused by all kinds of things. Normally, something that causes fading is another signal coming into play. Attenuation is when the signal weakens from moving away from it, and you correct that by amplifying it if it's an analog signal, or repeating it if you're dealing with a digital signal. And then noise. Noise is a big problem because You know, we've talked about how these lights put off noise into an unshielded cable. Solution with the wired is to shield it. You can't really shield a wireless signal, so you've got to deal with noise. Usually the only thing you can do with noise is eliminate it. Figure out whatever it is that's making the noise and take it out. All right, so 2.4 gigahertz is used for wireless, 2.4 to 2.4835 to be exact. There are 11 channels in that bandwidth. The problem with that bandwidth is that it is unlicensed. What that means is in unlicensed bandwidth, the FCC means you can transmit whatever you want in that frequency. If you've got a wireless signal and you've got a wireless access point, I can build a jammer and I can put it in my car and sit out in front of your house to stop your signal. And because it's unlicensed, there's really not much you can do about it. You can file a complaint and the cops are probably going to come make me move. Yeah. But ultimately, they can't put me in jail. I've done nothing wrong. 5 gigahertz band has 24 unlicensed channels. And that is used by N and by some of the A networks. And also, though some of that bandwidth is also licensed, it's used by weather and military radar. So what happens, you have all this frequency that's in use, and it's all divvied up to different people, so there's only little pieces of it that you get to use here and there. So the signals are either narrowband, broadband, or spread spectrum. Narrowband means you're going to concentrate the energy at a single frequency, a very small frequency. That means we're going to send out basically at one frequency and receive back at another one, probably a little higher or lower. Broadband gives higher throughput because we use multiple frequencies to transmit and receive, but less power is able to be given to each frequency. And it takes a little bit more of a more sophisticated of a transmitter to do that, or spread spectrum. Spread spectrum spreads it out and makes it random. This is what places like the state troopers have used now for their radios in their cars, because it makes it harder for somebody to listen in. If you think like 10, 15 years ago, maybe your grandmom or somebody had a scanner and would listen to the police in the area, and she knew everything that was going on because they only had one frequency. So they were transmitting and receiving on that one. All you had to do was listen. Nowadays, they've got these trunks that use multiple frequencies, and they randomly generate what frequency they're going to use. So it's a whole lot harder. You can't just have a scanner at home and listen anymore. What do y'all use? Do y'all just have one frequency, or do y'all use spread spectrum?
It's just a narrow band. Ours is just narrow band for us, but they don't really worry too much for that. They're not worried about the police scanners still use that spread spectrum.
Right. It's not that big of a security deal that somebody knows where a fire is, though, I guess.
People would probably rather know we were coming rather than not know, or knowing that we were coming.
Right, that's true. Yeah, I kind of agree. So there's different types of that too, and this is where you get more into acro. I don't think you're going to get this detailed on the test, but kind of be aware of it. FHSS is frequency hopping, and that's where it's random, and that adds security because the synchronization pattern is only known by the transmitter and the receiver. And you can change that. Like I know with the Motorola radios, like that some of the police and the military and all use, it's got a little key in it that's actually a little SD card, and the algorithm of what frequency to use is on that card. So every 2 or 3 years they can change that by having everybody bring their radio in and putting a new card in it to change the order. So that if somebody had figured it out over the course of listening to it long enough, you've shut them off because you've changed it again. Direct is easier to deal with, but direct just goes from one frequency to the next, to the next, to the next, to the next. Direct is not really used for security. It's used for more bandwidth by spreading it out and getting it out quicker. Here they're just showing an example. Here's a frequency hopping, and here's direct, just showing that they're going in order. All right, so another thing you have to deal with, especially now with wireless covering more areas, is fixed and mobile. If it's fixed communications, then the transmitter and the receiver don't move. That makes it easier to use directional antennas so you can get more bandwidth, but that makes it a bigger deal when something moves. The advantage of fixed is that you've got no wasted energy because you don't have to send signals out in ways they don't need to go. And it almost adds a little bit of security because you're not sending the signal out. If somebody's going to be spying on a direct signal, they've got to be close to where it's being sent or received at, which means you can watch for people like that, you know. But we now live in an area where people move around all the time. We move around with our laptops. People are on their phones in their cars. So things are more mobile. In dealing with wireless networks themselves, actually wireless in a computer, there are two basic types of networks, an ad hoc and an access point oriented. You probably will see a question on your test about an ad hoc network. And basically what you need to know is that an ad hoc network is one that doesn't have an access point. You can create an ad hoc just between two computers. If I needed to trade data with one of you, for example, and we didn't have an access point back there, we can make an ad hoc network. And just your computer could connect to mine through that network. Ad hocs, though, have poor performance because more than 2 or 3 users, and they get kind of rough because there's no central point managing everything. With an access point, which is often called an AP, the AP accepts all the signals and then retransmits it out to the network. And that is, another name for your AP is a base station, a wireless router, wireless gateway. You'll hear all of those used. So in setting up infrastructure networks, you set it where the stations communicate with the access point and not directly with each other. So that is what we have in here as an infrastructure WLAN. Even if all of you are on your computers right now and you're hooked to the wireless network back here, if my computer wants to communicate with your computer, it doesn't do it directly. My computer talks to the AP and the AP talks to you. WLANs can include several access points. Ours in here just has one because I'm just covering this room. But I could easily put one next door and one in the next classroom and make them one big network. BipsyLink is that way. BipsyLink is several access points that act as one that you connect to. And the maximum number varies based on what we're doing. It might be 10, it might be 100, it could be 1,000. Here they're showing just an example of an infrastructure LAN. You see they've got a switch that's wired going to an access point. Again, very seldomly do you find truly wireless networks. Usually wireless networks are going to have a wired component. Even at home, if you've got a cable modem and a wireless router, you've got a wired component in that there's probably an Ethernet cable running from your cable modem into your access point. All right, so mobile networking allows for roaming access point. And what that means is that if you have multiple access points, there's an algorithm that they will, if you put them on different channels, but you give them the same SSID, they can look for the strongest signal closest to them. And as you move out of the range of one into the range of the other one, your network will switch. What you do in a wireless environment for business where you want to cover a big, broad area, you wire the access points together up in your ceiling. And then as somebody moves from one to the other, there's no packet loss. It just switches access points that they use. BipsyLink is supposed to work that way, and it does pretty well, except they don't quite have enough. They didn't get enough money the first time they wanted to do their wireless. That's something that TechFee approved. They're supposed to be upgrading in the spring to a new wireless system. And they asked for a lot more access points. You really do need more than you realize, even in a... Bipsy's big, but it's relatively small as far as campus-wise. And I don't think they got anywhere near enough. One of my last projects over at LSUS was the wireless over there. And it took 127 access points to cover that campus. We had to put them everywhere. And things that we didn't take into consideration that luckily we had Cisco come in and they told us, and we should have thought about it but didn't. Those old buildings, most of the walls have got rebar in them. Your signal just will not go through those. So we had to put them much closer together than our original plan was over there to cover the area. And then we put a couple outside to cover, like in front of the student union and all. Generally your range for an access point with A, B, or G is about 300 feet. Other things, though, that you can do with wireless is use it to connect two wired networks together. One of the first wireless projects I did in Shreveport was for the juvenile court, and that was what we did. At the juvenile court, you've got the court in the front, then you've got an annex that's got more offices in it, and then they ran out of space. So there's actually two T buildings behind that each have 4 probation officers in them. And it shoots across the parking lot. So we didn't have wired connectivity out there. And other than them running a fiber all the way out to the T buildings, which would have either had to tear up a parking lot or go all the way down around it, what I did is put an access point in the 2nd floor in one of the windows and pointed it at the T building and put an access point in the T building in the window pointed back. And I put the LANs in access point mode where they would only respond to the MAC address of the other AP. So I basically made them a wired network by doing that. Then I put a switch inside of the T building and we hooked each of the computers to the switch. So that's connecting 2 LANs together. Now we didn't do it there, but you could use directional antennas specifically directed and go a lot further with it. In Ruston, they have an aviation program at LA Tech. So we had a need to have computers that were on the tech network at the airport. And the way that we accomplished that was by doing a wireless network with directional antennas. You know, I don't know how many of you have been to Tech before, but Tech's got Wiley Tower, 10, 16 stories up. We put one on the top of it. Then out at the airport, they've got all their communications equipment. So we stuck an antenna on the top of their tower and directed them at each other. And that was, I think, 3.5 air miles, and it worked just fine. And then we did something that wasn't kind of to spec, but it worked. If you ever find yourself in a need to come up with a cheap way to deal with lightning, because those were the tallest things around, we were worried about lightning hitting the antennas. So we didn't have the money to buy these $3,000 surge protectors they want for this wireless stuff to actually stop a lightning strike. So we bought 4 $100 media converters and converted it from copper coming out the AP into fiber and put a 400-foot fiber run in the middle of it and then back to copper on the other end. Guess what? Electricity won't follow copper. It's going to melt the wire, but it isn't going to blow the network up. So that was our very poor man's lightning corrector.
I like it.
It worked. It worked. All right, so WLANs have the support for the same protocols as wired LANs. And that's important because, you know, I've said this before, at layer 3, TCP/IP doesn't care what it's connected to. That way, if it's wired or wireless, because even though the lower layers 2 and 1 are going to be different, the way it talks out on the network is going to be the same. So your IP can go onto wired or wireless interchangeably. Here they're showing that. Here they've got 2 wireless LANs connected together. All right, so 802.11 is the common one. 802.11 standards to be aware of, the A, B, G, and N. They share some characteristics. They are half duplexing, and I'll explain how we get around that in a minute. Half duplexing means they can't transmit and receive at the same time. Wireless in general is that way on the same frequency. All right, they both use a MAC address that is the same physical addressing scheme as 802.3. What that means is that wireless has MAC addresses that are compatible with Ethernet MAC addresses, so that we don't have to convert between Ethernet and wireless when they're connected to the same network. That becomes important because, again, I said most people don't have pure wireless networks. You've got wired networks that have got MAC addresses on it that can then be transmitted out on wireless because they're using the same 48-bit scheme for your MAC addresses. Y'all all remember what a MAC address is and understand that part. Make sure I know you're going to get this question on the test. Make sure you know how to recognize a MAC address. They're probably going to give you a list and say which one is not valid, or pick the valid one out of these. One of them will probably have too many numbers in it. I can almost guarantee you one of them will have a character that's not a hexadecimal, like a J or an L or something. And then one will be completely off the wall. One will be an IP address. Do what? Yeah, 12 numbers. Yeah. And that's stuff like, I have to stop and think, because you don't, normally you don't use that every day, because, if a MAC address is wrong, it's just not going to work in whatever you're trying to put it in. If you're trying to block something by MAC address and you put a J in, the router is going to let you know very quickly you've done something wrong. All right, so wireless uses CSMA-CA. Because they don't deal with collisions very well, they minimize the potential for collision. And they use an acknowledgement to verify every single packet transmission. That requires more overhead than 802.3. 802.3 doesn't require an acknowledgement for every packet, but wireless does. That means the real throughput is far less than the theoretical maximum. If you have a G network at home, it's 54 megabit potential maximum. You're not going to get that out of it. Your computer might actually be transmitting 54 megabits, but by the time you add the overhead of all the acknowledgments, you're really getting more like 25 or 30. A general rule that I tell you to use, that I use, if you can do wired, do it. Wired is always going to be better than wireless. Wireless does have a great purpose, though, in that there are lots of places you just can't do wired. If you're working in a warehouse, you may be just absolutely, there's no way to run wire across the place. But if you can figure out a way to wire it, do wired, because it's going to be faster and it's going to be more reliable. They also use an RTS-CTS, which is a request to send and clear to send. It says optional, but almost all of them use this. This is efficient for large transmission packets, but it decreases the overall efficiency. What this does is an RTS is sent out on the network before data. Basically, you can almost think about this as in that three-step window. Remember when we were talking about connection-oriented protocols, we have that three-step process? Kind of the same thing here. An RTS is a request to send. The AP turns around and sends a clear to send. And once that clear to send is sent, none of the other devices will talk again until they see another RTS. So that way the channel's left clear for them to actually talk on it. Here they're just giving you a little kind of flow chart of showing how that works. If detected activity is found, it waits. If nothing's detected, it transmits an RTS, but it won't send data until it gets a CTS back. If it doesn't confirm the CTS, it waits and sends another RTS. All right, so there's a process called association. And association is where a packet is exchanged between the computer and the access point. The association is what then allows the computer to gain access to the network. They said internet here, but really it's network access. And that association packet is where the SSID comes in. And we'll talk more about the SSID in a minute, but that's the purpose of it. In scanning, you're looking for access points. There are two ways to scan. There is active and passive. And in passive, you're looking for the access point to send out what's called a beacon frame. And that beacon frame has the SSID of the access point in it. Most networks use the passive frame because the network, the access point, constantly is sending out data, even when nobody's listening, with beacon frames in them. I think they're sent like 90 a second. There's a bunch of them. But that's also why when you turn your computer on, it only takes a few milliseconds before you see all the available networks in the area, because they're all transmitting and you're looking for it. When you're in passive scanning mode, what your wireless card's doing is scanning all the channels real quick, looking for beacon frames and sticking them up there on your list to show that they're there. If the AP is not transmitting, then you have to probe, and a probe is where your computer sends out a packet and says, "Are you there?" and it will respond. Probes are only answered by the device with the proper SSID in them, though. So it's a way that people used to think you could kind of hide your network, and in a way you can hide it from Joe Blow being able to get on it, but it's very easy to use a network scanner and still see that data. Because the packets, even if you're not broadcasting your beacon, are going to have the SSID in it. So I could still gain access to your network that way. So the SSID is called the Service Set Identifier. And what it is it's a unique character string that identifies the access points. It is configured in the AP, and it allows for better security and easier network management. If you have more than one AP set up to use the same SSID, then it becomes called a BSS. And the BSS is a basic service set that is a group of APs using the same SSID. You don't really hear that term used a lot, but that's what's going on when you do that, when you set up a network that way. ESS is where you're setting up access points connected to the same LAN, and they share an ESS ID. That allows for roaming. That's where you move from one base station to another base station without losing connectivity. All right, so pluses to that, people can walk around your building. Here you can connect to BipsyLink and walk around and get on different networks. Minus is what's called a rogue access point. And a rogue access point is basically a man-in-the-middle attack. You know, earlier I was telling you all about the wireless, the 4G network they'd set up. Well, they were the strongest signal, so everybody connected to it. In ESS mode, your computers do that. So all I need to do if I want to try to hack the network is if I know BipsyLink is the right name and I can get on BipsyLink, then I set up an access point called BipsyLink, put it close to whoever I'm wanting to get data from, and have it repeat the data onto the real network, and then I log it all. I log all the data. Rogue access points used to be a big deal for networks because, you know, anybody can set one up. So here they're showing just a network with a single BSS ID. And here they've got multiple BSSs forming one ESS. All right, so association, we said, is the connection between an access point and a device. Reassociation happens when they move from one to another. Reassociation simply occurs when the error rate gets too high. A reassociation is sent out to make sure you're on the access point that you should be on. Okay, so 802.11 uses frames just like 802.3, but the additions are the acknowledgments, the probes, and the beacons. The 802.11 specifies the MAC sublayer frame type, which is very much like the 802.3 subtype that we looked at before. Medium access and data delivery is controlled by acknowledgment and RTS-CTS frames. Management is carried out by association and reassociation to the AP for the device. And then data is the carrier data between the stations. So here you see they look kind of the same, but the MAC headers are larger on an 802.11 frame than they are on 802.3. And the reason is because we've got extra information we need in there. We need a frame control. We're going to have a sequence. We're going to have a duration. And we're actually going to have extra MAC addresses. Anybody want to take a guess at why we got an extra MAC address in here? What device do I have in a wireless network I don't have in a wired? If two of you are going to communicate, what else has got a MAC address that's been thrown in the middle?
I think I know the answer, but I'm probably wrong.
Take a guess.
Talking about the actual transmitter itself? Or?
The access point, yes. The third MAC in this is the access point because it's got a MAC address.
That's what I was thinking, because a wireless router is actually a wireless transmitter and receiver, and then it has a switch and a router in it.
Yes, exactly.
Which will have a MAC address by itself.
It will. So that's what's been thrown in the middle. Now I've got a receiving MAC address, a destination MAC address, and an AP MAC address for the AP to respond to the packet. So that's why it's a little bit bigger. All right, so 4 frame fields: source address, transmitter address, receiver address, and destination address. Wi-Fi again shares MAC sublayer characteristics. Basically, if I go back to this picture, that's why they're so easily convertible between one and the other. What happens is the AP gets that and just strips the control and the extra MAC out and pops it out on the wired network. So it's very easy to convert between an Ethernet frame and an 802.11 frame. All right, so now the different standards. 802.11b is 2.4 gigahertz. 11 is the theoretical maximum, though what you normally get out of it is 5. 100 meters is the distance limit. It's the oldest, but it's the least expensive. Very few places are still using B. Almost everybody's moved to G or N. A came out after B. It uses the 5 gigahertz band, which is not as congested. Another thing that I didn't mention on 802.11b, in that 2.4 gigahertz band now, in addition to all these wireless networks, are all of these cordless telephones. So that's a very congested area. You get a lot of interference in there. So A came out. A had a 54 megahertz theoretical maximum, but what you really get out of it's about 11 to 18. However, because it was 5 gigahertz, because of the way the 5 gigahertz spectrum works, you can only go about 20 meters or so with it, and it stay at full speed. It requires additional access points because of that. Somewhere you did see A used a lot, though, was in line of sight to connect APs together. In my network over at LSUS that I was telling y'all earlier, the one access point that we put outside is not close to anything else. So in order to get it connected to the others, it's kind of in the middle of an area. And we put another one over close to a building. And those two communicate to each other on A. And then that one would communicate B and G with computers or people that are walking around out there outside of the student union. So that, because that one's not used by anything and it was line of sight, it's okay that it's a little over 20, but it's not as fast. People aren't downloading a lot of files out there. If they're surfing the internet outside at LSUS, chances are high they're, looking at the web or YouTube or checking on email or something simple. All right, I'm going to say G is probably still the most used one, even though N is quickly taking over. G, 54, but you actually get 20 to 25. It's also in the 2.4 gig range, and it's completely downward compatible with B. All B devices can connect to a G network unless you tell the G network to not answer B requests. And the reason that you may do that is because of speed. Wireless is one collision domain. So what does that tell you? In talking about speeds earlier in a hub, I told you, what about a device if it's slow? It's going to slow the whole network down. If you have one B device connected to a G network, the whole network is going to have to slow down to B. All right, N was finally standardized in 2009. The maximum theoretical is 600. In reality, what you get over it's about 100 to 150 if you're the only user on it. When you add users, it slows down. It is backwards compatible with A, G, and B. The same rule applies, though. If you buy an N network and you've got all G devices or one G device, it's going to slow down. So something they added with N, and I don't think these talk about it, but so you'll know about it if you go to buy an AP, they added what's called MIMO. MIMO is multi-in, multi-out, and what happens is that AP's got multiple transmitters and receivers in it. So now, because the AP acts like a switch as well, you can have users that are connected on G speeds to one antenna and users connected at N speeds to the other antenna. So now the whole network doesn't have to slow down when those one older connections go in. And when they first came out with MIMO, they were expensive. They were like $200 or $300 for access points. Now, I think they're only about $30 more than just an AP. If I were going out right now to Best Buy to buy one, I would buy a MIMO one because I still have devices that are G, like this laptop, but I have some stuff that's N, so I want my N stuff to connect it in.
I just bought one for the station. There was a wireless in that had, you could program it for 5 megahertz, and then over here you could do the 2.4, so you could actually run.
Yeah, it's probably MIMO then if it's got the two different settings. Most of the MIMO ones, if they have external antennas, you can spot them because they're going to have 3. They'll have 2 antennas for N, and then they'll have 1 for A, B, and G. All right, so N uses 2.4 or 5. Actually, they did mention it. I didn't know this was in the slide. It shows I hadn't been doing my homework, doesn't it? MIMO is multiple in, multiple out. Another thing you can do with an N network is called channel bonding. And that's where you take 2 of the channels and put them together to make one wider channel. So basically, you double the bandwidth available on a single channel on an N network. They also use higher modulation rates. That means they make more efficient use of smaller channels, and they use different encoding. All right, here they're showing frame aggregation. So with N, what that means is we combine multiple frames into one larger frame. Earlier, you saw the MAC header for wireless has got that extra MAC address in it. A, B, and G all use the same size packet that Ethernet uses, so they've added that overhead. Well, with frame aggregation, what you do with N is if it realizes there's a solid signal, it changes the size of the frame every time. If it sees that it can send like 10K at one time and the other device receive it and respond to it, it'll send 10K packets every time with just one header to each one. The plus to that is faster if it's a clear channel. The minus is as the channel starts getting corrupted, there's a lot of retransmits. In A, B, and G, I'm only retransmitting that 1K or that 4K piece of data. Here I've got a 10K piece of data to deal with. So, and they don't get into it, but what that's called is sliding windows. And what that means is you change the size of that based on how the data is. So here with N, they're saying maximum throughput depends on the type of channel and what you're actually using, 65 to 600. Not all 802.11n features are backwards compatible. This is a great little slide, and this is what, if I were you, I'd take away from this chapter. Kind of memorize the frequency range, the standard, and I wouldn't worry about the effective throughput, but know the theoretical maximum. You're probably going to get a question where they say, this particular wireless technology will connect at 11 megabits and is a 2.4 gigahertz, uses 2.4 gigahertz frequency. And then they're going to give you a list, A, B, G, or N, pick which one it is. Questions like that.
I think on the cram master, you have about distances, like certain, like what is G versus N or something.
I would know the distances too. That's a good one, and that was on there. All right, so wireless LANs at home, it's pretty simple. If you're going to install a corporate-wide wireless network, you really have to stop and think about how you're going to design your network, because there are some problems you can run into. With one access point, it's pretty easy. You don't have to worry a lot about it. They're combined with switching and routing in a lot of cases. At home, like I said, it's not uncommon for you to have an access point that's also your cable modem or your DSL modem, probably a 4-port switch on the back, and it's your router and your firewall for your network. In that case, it's also going to act as an internet gateway. In most businesses, however, you're going to find that the opposite's the case. What they're going to have are these access points that are called dumb APs or dummy APs. And the AP itself doesn't do anything, but they're going to have some sort of control module that controls those access points. I know like at at LSUS, we use Cisco stuff. And in the Cisco world, what you have is a device called a WISM. And that WISM is just a computer But every time those access points are rebooted, they start completely from scratch. They don't have any configuration on them. They send a request to the WISM and get their configuration file every time. And the reason that's cool and good for a big place like that is, let's say we want to change the SSID at LSU. LSU, for some reason, changes their name tomorrow and becomes BIPSI Shreveport. All we'd have to do is make one change in one configuration file and then reboot all the routers on the campus, and they'd all pick up the new file. So changes on a network that's big like that are much easier with this. If we'd use traditional APs, then somebody'd have to log into 127 different web addresses, change the data, and reboot the routers. So it would take, I mean, it's doable, but it would take somebody probably 2 or 3 days, whereas it's a 20-minute ordeal to change a file and reboot everything.
One good example, I just got through, I'm doing some internship with an IT company that does different stuff, but one of the clients is Samstown, and they do all the wireless network for Samstown. And we had to go in and do some repairs on some of the APs that were in each one of the rooms. Of course, most of them were just a problem where they were unplugged, so you just plug them back in and go. But it's the same difference when they put in a new AP. You have to go in, you have to set everything, other than the MAC address, you set all the IP stuff. So if you were to, again, what you're talking about, if you were to do all of them, you would have to go to each room.
Exactly, it's such a pain.
It's amazing that they do it, but they pay $90 an hour to do it.
Right. Yeah, which is insane, but they've got it, exactly. All right, so here they're just showing a home office. They've got an internet, cable modem, a wireless AP connected to a user. Larger networks, you're going to have a systematic approach, and something you're probably going to do before you start is a site survey. And a site survey is basically exactly what it sounds like. Either you or you pay someone to go in and look at all of the characteristics of the buildings and determine how many you need. This is where having Cisco come in over at LSUS saved our bacon, because their site survey realized the walls were not, were old and that we're going to need extra APs. If it's a new building and you're doing it yourself and it's a small to medium company, a site survey might just be as simple as you put an AP in one corner and walk around with your laptop and see if it covers everybody, to determine if you need 1 or 2 or whatever. And you get really intricate. They make software now. You can download Cisco, HP, Juniper, all of them have their own version of this, where you, if you're dealing with a truly huge wireless project and you feed the schematics of the building into this software, and then you tell it what the composition of each of the walls are made of, and you can play with access placement on the software, and it shows you where the signals will go. All right, so with enterprise-wide, you're going to have to figure out how you're going to integrate the LAN with it. In most enterprise-wide WLANs, you're going to have wired running in the background that the wireless is going to be in front of. Here they're showing an example of that. They've got 2 APs and a router. All right, configuring devices. And we've run out of time, but I've only got a few more slides. If y'all want to stick around about 5 minutes, I'll finish it up. All right, with most home devices now, they've made it very, very easy to set them up. One problem was, in the old days, you'd get a device and you'd bring it home and plug it in, and it worked, but there was no security on it. The default network name was Linksys. It didn't have a password, and if you connected to it, it worked. Well, that was amazing and wonderful for Grandma who just got an iPhone and doesn't know how to use it. But it's sad because now Grandma's network is open, and if I want to download torrents, guess what I'm going to do? I'm going to connect to Grandma's network so that the FBI knocks on her door. So now they've come up with several different ways to handle this. D-Link, for example, they put a little card, a little business card on the bottom of all of theirs that has a random number on it. Cisco has a line called a Valet that actually comes with a USB stick. And you set the access points configured, you take the USB stick and put in your computer. And it loads the settings off of it. I know some of the Linksys stuff, it's got a button on the top of it. You push the button, and then you go to the computer, and it'll give you a code you type in, and that puts it on the network. So the whole idea is to try to make this more secure so that, I've said this a lot in this class before, I don't think people mean to not be security minded. You know to lock your door when you leave the house. People just don't know to lock their electronic door when they leave their house, and it's kind of that same thing. All right, in Linux, the command is iwconfig to view the wireless perimeters. In Windows, you can do it with your ipconfig command, your normal ipconfig command. This is the output of iwconfig on a Linux machine. All right, so things that happen, make sure the SSIDs are the same. If you type the SSID in manually and you typed it wrong in the computer versus the access point, they're not going to be able to communicate. Make sure you have the same type of encryption. The channel and frequency, not so much because they're auto set in most cases, but if you set it to one specifically, you got to match it on the client. And a standard mismatch. If you've got a G network and you've told it to only accept G requests and you have a B device, your B device isn't going to be able to communicate. Verify the antenna placement. Check for EMI sources. That's a big thing with wireless. Noise is a problem and there's no fix to noise. You just got to move the noise. All right, so a final technology is wireless broadband. And this is for your high-speed, high output devices. One of these that's becoming popular is WiMAX, and it's worldwide interoperability for microwave access. WiMAX uses 802.16e or 16m based on which one you're looking at. 2 to 11 or 11 to 66 gigahertz, and it has licensed and non-licensed frequencies. With fixed antennas, it transmits 30 miles. With mobile antennas, it transmits 10 miles. Something that's going to be fun to watch, and it's not going to happen in this class and maybe not in the spring, but by the fall, this is a technology to watch. Google just got approval from the FCC to go in with DirecTV, and they're going to start releasing a WiMAX type phone. And their idea, I think, is to actually enter the cell phone market, not as an Android device, but as a carrier. I think very soon you're going to be able to have Google as your phone carrier instead of Verizon or Microsoft. Plus and minus, you know, I think it's going to be super fast and cheap, but do you trust Google with all your data? Which most of us already have so much on Google at this point that it doesn't matter. But with an antenna mobile, you can get 10 miles out of it and still get a huge frequency. Maximum throughput moving is 120 down and 60 up. So we're talking about speeds that are, you know, pretty fast, especially at 10 miles going 60 miles down the road. One of the reasons that I think that Google's looking at this frequency, for one, it's not used a lot, and number two, you know, think about covering Shreveport with cell phone antennas. You got to have towers everywhere. 10 to 30 miles, you're not going to have to put that many antennas to get started. And they've teamed up with DirecTV. I think the backup is going to be satellite. I think that DirecTV's got a WiMAX satellite launched that they're going to connect to, and that's how they're going to sell it. I would never say it just covered one city. You'd never switch to it because, well, what do you do when you leave that city? But if you find out, oh, it's got a satellite backup link so I can still use my phone everywhere, right, then people will consider it.
What is the Bluebird wireless in the spectrum of this?
I believe Bluebird is the old E WiMAX, but I'm not certain. I'm pretty certain it's E WiMAX.
We use Bluebird at the fire station. That's what's become Ben because they don't have other than AT&T DSL, but they don't have cable anymore.
Right.
But I had asked them at that. They may not have known. That may have been what it was. They didn't know. I asked them if it was WiMAX, and they said no, but I'm not sure if he actually knew.
It may not be, but unless it's a licensed bandwidth number, it's probably E WiMAX, which E stationary, I mean, I don't know how much bandwidth you're paying for, but you can get about 20 megs, 25 megs out of it.
Okay. Well, they give it to us free because they lease our tower, so they give us free internet, and I think we've got it for like 7 megabits.
Oh, that's a good trade for y'all then. Y'all get free internet, and they're using the tower.
$600 package.
Right.
We get free 2 stations.
Here they're showing with WiMAX, this is one of the things you've got to have your antennas. where is y'all's in? Well, y'all are getting it probably directly off their antenna, but I bet it's mounted just above the tree line, isn't it?
We had, actually, we have our antennas probably like 120 foot antenna, and they got at the top of that, and then we have a radio in the office that actually picks it up. So it has an antenna that goes here. It's not wired directly to that, but nonetheless, it's stationary and it hits from there.
Yeah. Does it look like that?
Smaller, but nonetheless, it's similar to that.
Yeah, that's one of the old E ones.
Mm-hmm.
Cellular is something that's taken off now. 1G cellular was analog. There was no data in it. 2G, you had 240K data capabilities. 3G, 384. And now we're moving into the 4G world, and in the 4G world, it's an all-IP network. This is something that is making cellular take a big spot now, because the cellular networks are able to, with 4G, they're able to communicate with all kinds of IP stuff. All right, so with cellular, you have cell sizes. And these cell sizes change on access method. The population is a big one, and the amount of traffic. When you get outside of Shreveport, for example, the cell sizes are a lot larger. Like if you're going down I-20, when you get over to like Minden and that area, the cell sizes are bigger because there's not as many people using it at one time. If you get over here into the heart of Shreveport and Bossier, into the big populated areas, the cell sizes are really small because there's so many people on their cell phones at one time. Like, think about how many people are probably using a cell phone in Shreveport and Bossier at 5 o'clock in the afternoon. You need those small cell sizes because a lot of folks are on their phones. And here they call them cells because they look just like that. They're honeycomb connections. They showed them as butting up to each other, but what actually happens is they overlap a tiny bit, and as you move from one to another, the cell will move you to the next tower. Here are just some of the different technologies that are involved in these. 4G, LTE, and WiMAX are both packet. 4G LTE has a theoretical maximum throughput of 1 gigabyte, which is why it's so popular. But 500 is actually usable out of it. 4G WiMAX at 16M, you know, about 120 megabits, with 60 being the most maximum. And then 16E, the older one, 70, but you actually got 70 out of it. And then with 3G Plus, which this gets into a whole new fun area of lawsuits that I could do a whole class on with y'all. 3G Plus is what AT&T actually calls 4G. If you're an AT&T customer and you had an old Apple and you updated to iOS 6, you know, it all of a sudden started showing 4G. Well, what you're actually connected to is a 3G HSPA Plus network. And cell phone companies being competitive and snippy with each other, Verizon has now sued Apple, or sued AT&T over their phone showing 4G even though it's not 4G. This is why this is how Google is suing Apple. Google owns Motorola, and Motorola owns a patent to a type of transmission technology used in the 4G LTE network. And they're saying that Apple didn't license it from Motorola to put in their phones. So Google is suing Apple based on that patent. That's where all of this is. You know, I told y'all earlier I was going to have my class do this suit, my 210 class, about everybody suing everybody. That's where it's coming from. All right, so the last one we got is satellite. Satellite delivers television, voice, cellular. Satellites are great, but one problem with satellite that you hear a lot about is latency. No matter what we do, if you live in an area where you can't get anything else, satellite's better than dial-up, but there is an amount of time it takes to send a signal to a satellite and back. And the reason for that is, you'll see in just a minute, with the way that the satellite is connected. Let me find it here. Geosynchronous Earth orbit satellites. Those are very high above the Earth. And basically they're at the edge of where gravity, the Earth's gravity hits. And they fall around the Earth at the same rate the Earth is spinning. I don't remember the exact number. It's 22,600 and something miles. Well, no matter what we do, if you've got satellite and you got to send a data packet 22,600 miles up and back down to Earth, there's going to be delay in it. I had satellite in Ruston because I lived right outside of town at the end of Tech Farm and had no other option. It was great because it was high speed. Downloads were great. I couldn't play a game on it to save my life because the latency was too much for a game in setting up the connection to send all that data. You won't need to know this, but here's some of the different frequencies used in satellite. There are lots of other ones. You do different uplink and downlink bands. Like I said earlier, we use KU and KA to uplink to a lot of satellites, but most downlink at something else like L-band. Satellite internet is typically asymmetrical. That means the downlink is a lot better than the uplink. Here they're showing an example of it. And that is a quick summary of Chapter 8. Do y'all have any questions?